What we're going to do here today is just have a look and do a bit of a comparison on the oscilloscope as to the output signal and the different types of outputs that each of them have. So the first one we're going to have a look at is the Velleman, which is the smaller of the three. Now they're all function generators, but this particular one is more classed as a signal generator, but it does have 4 different outputs. You do have amplitude adjustment to some degree, but it's only fixed frequency, and it's run off a 555 timer, and frequency selection is through these pins here, and the output is right there. So you've got ground and you've got positive. We've attached our power supply. We're just using a 9-volt battery, and when we've got the oscilloscope attached, and we've got the amplitude turned right down at the moment. So the first signal we're going to have a look at is the sine wave. So what we'll do here, we'll just turn up the amplitude for the sine wave. And you see you've got fairly good and fine control, but you don't have a lot of output level, but it's handy for an amplifier or something like that, where you're going to get a significant amount of gain. Alright, so what we've got shown on the oscilloscope, we've got 200 millivolts per division. We've got 1, 2, 3, 4 divisions. So you've got 800 millivolts of output on the sine wave. If we expand the sine wave out, you see we've got a fairly clean signal there. It's not really going into distortion, and that's at maximum amplitude. So that's the sine wave. Now we'll have a look at the next one. So we just moved the contacts down to the next one, and this one you can see we've got a sawtooth waveform, and you can see we've got 1, 2, 3, 4, 4.4 divisions at 100 millivolts, so 440 millivolts approximately is maximum amplitude. And you can also see here that the frequency kind of sits at about 1.2k or 1.25k hertz. So a fairly clean signal. We'll spread it out a bit and we'll see what it looks like. And well, we're just going into a little bit of distortion there, but it's hard to tell. Looking pretty sharp and pretty clean for just a simple circuit. Alright, we'll move on to the next one. So this is the third waveform that they're actually supplying. This particular one is what they call their integrated waveform. You can tell by this shape here and rise and fall. We're on 500 millivolts per division. We've got 1, 2, 3, 3.2 divisions. So you multiply that by 500 millivolts and that'll give you your voltage out. So that goes 1 volt, 1.5 volts approximately, or a bit over 1.5 volts. We're still on 200 microseconds as we've been all the way through, and you can see here we're still reading about 1.25 kilohertz. It's supposed to be a 1 kilohertz output, but you know, you are going to get variation probably in these kits, and you could adjust that, you know, if you want to put some variable resistors in for the 555 timer and get that spot on. So I'll just expand that again just to have a look at how that looks. You can see it's holding shape fairly well. Close it up. It's a pretty sharp signal. So not bad for just a 555 timer and a few supporting components. So our last signal as far as the Velleman unit goes is a 2.8, right, 2.8 at 200 millivolts, 500 odd millivolts of output here. You can see you've got a little bit of overshoot and a little bit of non-linearity in the rise area here, and we'll expand that out and look at that and see what that's like. Our frequency here is reading 1.248, and you'll see as we expand it out, if we line that up on there and there, you basically got one division. So you've got about 400 nanoseconds of rise time, and then it does overshoot a bit and then come back down to a stable state. But that's not too bad for such a simple circuit. And you can see the overshoot there. Not really going into ringing, it's just a bit of overshoot. And if you bring it back, you can see you got a reasonable square wave out of there, but certainly something that you can play around with on circuits. So that's the Velleman. Simple. I think it's relatively effective, and you'll be able to do a fair bit with it. The next one we're going to have a look at is the Elenco Function Generator. This is the model FG-500. It's running off basically one IC, and the IC is an XR2206, a few biasing components and frequency selection components. But other than that, that's about all that's in this whole box. So it's just a one IC that's doing all the work. You can see here, you got your earth, you got a square wave output, and you got your sine wave and sawtooth. You got amplitude adjustment, you got frequency selection on this one, basically from 10 Hz to 1 meg, and you also got fine control for frequency. Alright, so what we've done is we've set up for 10 Hz, and when you touch it you get a bit of interference. We've got the amplitude on about quarter, and we've got the fine tune almost to the top. You can see here that it's showing 10 Hz, and we're on 20 milliseconds per division, and we're on 200 millivolts per division, and we can increase that amplitude and we can bring that up a lot, so we'll just keep it on about that. And you see, you can also see that when you're adjusting that you'll get a bit of noise, but the thing I'll show you is here on the fine control. If I turn that fine control down, you'll see that the frequency basically drops down to 0. So that fine control is how you're setting up the frequency that you're on. So we get that set up for 10 Hz again, and you're almost at the top of the range, and then it jumps a lot. So you just got to be careful when you're setting that up, and just let it settle. And that's on 10 Hz there, that's where we were before. So if I now switch that to 100, you can see that I'm getting slightly over 100, so again you can use your fine control to bring that back down. So it's a little bit temperamental in that area with reference to getting the frequency spot on. Amplitude can be turned right up, as you can see, that's at maximum, and if we increase the volts per division, there's a little bit of distortion when you're overdriving it too, and that's another thing you got to be careful of. But we've got 1 volt per division, and we've got 1, 2, 3, 4, 5, 5.6 right divisions. So you got, well, just under 6 volts, being pumped out there. But if I turn that down, you can see it starts to shape up the sine wave. So it's a matter of getting it to a point where you get a good sine wave at the right amplitude, and that's about halfway there. I'll put it exactly on halfway, and the frequency is reading 109.10 at 100, so you just got to play around with that a little bit. You can see there that we're 105 now, 104. So you can get on frequency, but it is a little bit temperamental. We'll go up to 1K. And the signal's still looking pretty good. We're on about half amplitude there, and we've got that set up. We're reading 951, so you just need to adjust up a bit. Go up to 10k. Still looking reasonably clean. You've got a little bit of noise or distortion down there. And again, that's on about half amplitude. If I increase the amplitude, you can see we're starting to go into overdrive. It's a matter of just finding the right position. And you're still getting that little bit of noise or interference there. No, it's not changing, so you can drive that up to, yeah, starting to flatten off top and bottom there. And we're just a little bit over halfway, so it looks like halfway seems to be a good point to keep your amplitude. Your frequency's 9.52k hertz, and you can see that is a little bit fiddly, but with a little bit of patience you can get it down to frequency 100k. Expand that out, and you start to get a little bit of distortion on the bottom there. Might have to drop the amplitude. No, we've still got the same problem. So you can see there on 100k we're getting this distortion down on the bottom edge, and we're actually at 94k there. So if we increase the frequency, it does take a little bit of time to settle down, but as you can see now we're up around the 100k mark. We're getting a good top area, but we're getting a little bit of distortion down the bottom edge of the waveform, and we're still not exactly on 100k yet. Oh, there we go. And if we go to 1 meg, right, you can see the amplitude drops right off, and we go to 1 meg. We've got the amplitude right up now. You can see we're getting a little bit of distortion in the waveform, this time on the top edge. So if we go from that to triangle wave, you can see you get a lot more output. And if we increase our volts, now we're driving a sine wave. Right, so we're getting a sine wave on the triangle wave output. So that's interesting. And we've got this at maximum, the amplitude's still at maximum. So the amplitude's not changing much there. We're still reading just a fraction over 1 meg. So if we drop that down to 1k, bring our sine wave, oh here we go. Now we're going into more of a triangle wave, pretty much on about half amplitude there. Frequency is supposed to be 100k, we're slightly over, so 116. A little bit of distortion in the triangle wave at 100k, that's about half amplitude. So about half amplitude looks pretty good. Now we're at 10k, so I'll have to, that looks a bit sharper. Yeah, 9.98 there. So that's looking like a better triangle. If we overdrive it, it seems to hold alright, so that's maximum there. And we can take that down to minimum, and it disappears, but leave that on about halfway. That's halfway there. We're on 1 volt per division, and we're getting about 1, 2, 3, 4 divisions. Right, so that's 4 volts of output. You got it, you know, at that level. Take it down to 1k. Still looking like a pretty good triangle waveform. And amplitude, you can see it rounds off a bit at the top if you overdrive it. Take it down to about halfway, seem to be fairly good. And our frequency is just a bit over 1k. We could drop that down slightly. You've got to let it settle a bit. It's fairly touchy on the frequency fine control, as with all the settings. And now we'll go down to 100 hertz, so we'll see what that looks like. Finding a little bit of a rise time here, on the 100 hertz. It's not looking too bad for, for the circuit itself. We increase the amplitude, you can see you can just slightly overdrive it back to about halfway. quarter way, you can take it right down to nothing. So it's about halfway on the amplitude, seems to be a good position to leave it in. Fine control, again we're a bit over frequency, so we can drop the frequency down a bit. 99, pretty close. Now we'll go right down to the bottom, see what that looks like, and it doesn't look like a triangle. So that's down at 10 Hertz. We're reading 8 Hertz there, so we'll just bump it a bit, see if we can get up to 10 Hertz. Yeah, there's 10 Hertz, it's close enough. We're down to 10 Hertz, we're on mid amplitude, we can take that amplitude down, which looks more of a triangle. And if we increase it, I think we're going into something that's not a triangle waveform. So we brought it right down. If I increase the amplitude, the volts per division, so decrease them so we can see what it is. Yeah, it's not too bad, but we're on 50 millivolts per division, and we're looking at 1, 2, 3, 4, 4.5 divisions. So you'd have to turn the amplitude right down to get that triangle wave. Depending on what you're doing, that could be suitable, but you've got to be aware of the limitations, of the unit itself. We just moved over to square wave. We're on 10. The frequency is showing 11, and you can see it doesn't look anything like a square wave. And if I increase the amplitude, decrease the amplitude, it's not showing any change at all. We can adjust the frequency, so the frequency fine tune works. So at 10 Hertz it's looking like a pretty poor square wave. We'll go up to 100 Hertz and we'll expand that out. You've got a rise time, and it decays, drops, and then you've got this odd shape here, which is definitely not a square wave. Amplitude doesn't change it. It's looks like it's a pretty preset amplitude. Let's go to 1K and expand that out. Now it's starting to look like a square wave, but it's definitely looking a lot better at that 1K range. So I'd say basically 1K onwards you'd probably get a good square wave. We'll see how far we go before it goes into distortion again. Go 10K, still looking reasonably good. 100K, let's have a look at that one. And now we're going back into distortion again. So you can see here we're definitely not getting a proper square wave. We've got a long rise time here and a very good back edge, but the front edge is certainly not doing anything. And if we go up to 1 meg, right, you can see here that we're definitely not getting a square wave. And our voltage is dropping off, so we'll increase the voltage a bit, but I think we can ascertain that's no square wave. So I think that square wave area is really that 1K probably to 10K. Yeah, you see you start going to distortion. So we're at 1K but at a frequency of 90, like 90 Hertz there. Starting to flatten out top and bottom, and still a little bit of curvature there. So you're around about that, say 300 Hertz I'd say. So probably 300 Hertz up to, if we take it to 10K, showing just a little bit of rounding off on the top edge of your square wave. We take it down to the lower frequency of that range, and we expand that out. Should be pretty sharp, so that's about 900 Hertz. So there are some limitations with this. You'd have to map that out and be aware of it, but other than that, it's workable. So what we have here is the Jameco Function Generator. This is a 20685, is their part number for it. So this one is working on the XR2206, the same as the Elenco Function Generator it was using. So be interested to see how this one turns out. The major component in this is the IC. The rest of it is just peripheral for biasing and frequency selection. This has a bit of a different setup. You've got a switch here for your triangle sine wave output. Square wave outputs are up here. You have frequency adjustment, you have amplitude adjustment, you also have frequency range, and you have frequency sweep input if you were wanting to put a sweep in there, and you have amplitude modulation which you can put in as well. Now we won't be using the amplitude modulation, we won't be looking at the frequency sweep input. I just want to see how it goes with its output. So at the moment we've got it set on sine wave. We've got the frequency adjust it down, and you can see here we're only reading about 2 Hertz. Well, we're picking up interference there. You can see on there we're picking up 2 Hertz, and we're at 200 millivolts per division, 200 milliseconds per division as well. So if I increase the frequency, you can see that the frequency increases, as I adjust the potentiometer around. And if you look at that, we're now on 111 Hertz, so we've significantly increased from 2 Hertz. And if I spread that out a bit more, let's just see what that looks like in real time. Change my volts per division so I can see it, and you're looking at a pretty clean signal at that level. So let's have a look at that as we bring it down. Obviously the frequency is going to change a lot, keep adjusting that as well, but we're looking at a pretty clean signal. It's just noise from the pot being adjusted, I'd say, but your amplitude level is going down, as you're adjusting it. About halfway. We'll see what we got there. We'll have to decrease the amplitude so we can see it, and we're still looking at a pretty good sine wave. That's on your first frequency range. So if we adjust that all the way down back to where we were, amplitude adjustment on here, we found that you can see there we're taking it down, and this is increasing. Now we're starting to go into distortion because we're overdriving the right chip. And we found that about halfway was probably the best point, and you just adjust that either way. One thing that we did find with the amplitude adjustment as far as the circuit goes is that the way they had it wired up in the schematic is the way we wired it up here, and it operates in reverse to what we have it marked here. So as you go right clockwise, it reduces, and as you go anti-clockwise, it increases. So you just got to be aware of that. We could change that over, but I'm not really that worried about it. Alright, so we'll go to our next frequency selection. You can see here frequency is increased, also the amplitude of the frequency is increased. So we'll just bring that down so we can see it, and we'll expand that out so we can look at it. And that's at frequency adjust minimum, so you can see here. And if I bring that up, right, you can see the frequency is increasing. It's holding a fairly good frequency so far, and we'll bring it right up to the top, and I'll have to expand that out again so we can see it. But we're looking at a pretty clean signal, right? And now we're at a bit over 1 kilohertz there. So this range here is basically 1 kilohertz, and if I take it right down to the bottom, that's about 11 hertz. If I go to the next frequency range, I'm at the minimum there. Just get it back in focus. Yep. So we're at 105 hertz there, and if I increase the frequency at that range, it goes from basically 105 through to 10k, a bit over 10k. So if I expand the 10k out, let's have a look at that and see how clean that is. Starting to show probably similar to what the other one had, that little bit of distortion using the same chip, but overall not too bad. So that's at maximum, and if we take that right down to minimum again and bring it back into, you can see that we don't have that distortion there, so we're picking up something. I'll just increase the voltage a bit. So we're at 2 volts per division now. You can see we're back to 105 hertz. And the last range, right, expand that out. Looking, yeah, look pretty good. Not sure what this is down here. It could be a bit of noise we're picking up. If I increase the frequency on that, we're starting at basically 1 kilohertz, and that should go up to 100k. which is where it should be. Expand the 100k out, what's that look like? And a little bit of noise or distortion. A little bit of noise at the top, but it shows up more at the bottom there. And that's the last of the frequencies, so that one goes up to 100k. And that's the other thing that was interesting too. You know, they give you a 6 right position switch, and you're only actually using 4 of the positions. Alright, so we've taken it back down to right position 1. I'll take the amplitude back down. We'll have to reduce the volts to see what we're looking at. Alright, so that's the sine wave, so now we'll flick over to triangle. See, you seem to get that same interference when you touch certain things on the box like that. So it picks up noise very easily. Alright, so now we're in triangle wave, and that's at the lowest frequency, which is showing around about 20 odd hertz. So I think it's a bit unstable, it's jumping all over the place. But that's the triangle output, apparently. So we'll increase that and we'll see how we go. So I'm going to take that up to the maximum area. We'll expand that out, see if we do have a triangle wave. We've certainly got a lot stronger signal, and we'll have to increase the volts, see what we're looking at. So that's it there. And you can see that we're on maximum frequency adjustment. Now we're looking at 112 hertz. We've got distortion top bottom. We're on 2 volts per division. Still seeing this distortion, so let's play with our amplitude and see if we get anything there. We'll take the amplitude right down. No. Take the amplitude all the way up. No, and we're still getting that distortion. So at the minimum frequency, you can see here on 10 hertz. So if I start increasing that frequency, I think that's where you're going to see things starting to shape up, and as you can see there, it does. And we're starting to get that triangle waveform, which we should be getting. And we'll expand that out. It's still not quite right. And we'll take it all the way up. Keep going the wrong way. And we're still not getting a good. Triangle waveform. And now we're reading, like 1k hertz. So we'll adjust the amplitude. See if that does anything. There you go. So you need to work with your amplitude, right, with reference to your frequency adjustment. So if we drop that down to the lowest point and go back out, will that make any difference? So if we adjust the amplitude here, no, it's not gonna fix it. And if we go the other way, we go in distortion. So we're still not at that point where we got that clean signal. So we'll just keep increasing the frequency. Alright, so we're a bit higher now. See if we can get it to shape up. No, still going more of an integrated waveform. Just kind of missing it there. Increase the frequency. Now we're starting to get that clean triangle. So that's about 71 hertz, which is not too bad. Expand that out. Probably see there's a little bit of integration there. There's a curve in the signal. We'll adjust the, we're still seeing that. And if you drive it too far, you're going into right distortion there. So we'll just increase the signal a little bit more. Get that there. So I'd say about 100 hertz is where you're going to start to see a clean triangle waveform, which is what you're after. And as you can see here, we've got to adjust amplitude as well as frequency range. So that's on your second position. So we're basically at about 100 Hertz to get a clean triangle. If we go to the next position, we'll just take that all the way down. So you can see there that you've got a pretty clean triangle there. We haven't touched the amplitude from that point. And if we increase that all the way up and we expand that out, see how clean it is. It's still looking pretty good. Haven't touched the amplitude again. So on the third position, you know, at frequency adjust max, we're at around about 10 kilohertz. So that's not too bad. So we'll go to the next position and we'll take it down. We should still be seeing a pretty sharp triangle waveform. Now we're at 1 kHz, and if we increase that all the way up to the top end and expand out the frequency, not as good right at the top end. It is a like a sawtooth waveform, a little bit of distortion top bottom. Whether we can get that out through dropping, yeah, we can just, but we're losing amplitude. So again, it's a little bit of playing around with amplitude and your frequency at the top end to get a result. So that's about where it stands with those ones. Now the last output we're going to have a look at is our square wave, and some interesting things happen there. We've got our volts and 5 volts per division. We're looking at about 1 Hertz. So and what we're getting is basically differentiation. You know, where you're getting a sharp pulse coming out around 200 milliseconds. So if we start increasing the frequency, we'll take that right up. You can see the frequency is increasing. I'll have to expand that out again, see what we're getting. And we're still not getting a great square wave at that point, but that may be adjustable. Now notice here that we don't have any adjustment at all. Alright, so the adjustment here doesn't play any part. So we'll bring that right down the bottom again, and we'll go up to the next range. Right, we're sitting at 10 Hertz again, and we're going to increase the frequency. Now we're starting to see a square wave. So we're at around about, let's see how low we can go. Still square wave, yeah, looks reasonable. Yeah, a little bit of distortion there. Probably about 200 Hertz and upwards. Alright, if we go to the maximum, we're at 1 kHz. We can expand that out. And there you go there. So now this has two outputs. It has full swing and half swing. So this is full swing, right, or what they call full swing. We'll go to our next position. So we'll turn that all the way down again. Turn it up another one. Close that down, and again we're kind of below where we should be. We're only at about 170 Hertz or thereabouts, but if we increase that to, say, so you can see it's right taking shape there as we increase the frequency, starting to get pretty close to a full swing around about 200 Hertz where we said before. Now we'll take it all the way up and expand that out, and we're starting to get a little bit of rounding off, you know, on the leading edge. And that frequency, we're at 10 kilohertz. So at 10 kilohertz you kind of have a square wave, but you got a bit of rounding off at the edge there. We could expand that out and see well, you know, like what that's like. But again, amplitude doesn't play any part in this now. You know, just kind of re-emphasizing that. So we'll take that right down, and we'll go to the last position. And now we're at 1.8K, you know, at the minimum frequency. You can see we've got a pretty good square wave. And as you go up, somewhere around about 10k or thereabouts. I think we start to see that distortion. Probably seeing a little bit there. Bit hard to tell. Go up to there. Still looking pretty good for a square wave. 4, 6. Now we're starting to get into some problems. Now we're up around about 50 kilohertz. We'll just take that down. See where we can find our maximum. Bit under 10k. Probably, I mean, you probably call that a square wave, but there is a little bit of rounding off at the leading edge. So what they mean by half swing is that we're only getting half the voltage level from that edge to that edge. That's their half swing. Otherwise, if you go into full swing, you're getting twice that voltage level. But it's going to work on pretty much the same principle as we saw before with the other square wave. It's got a certain range that will work in, I think, pretty well, but then it'll go in distortion at one end or the other end. So that's the Jameco Function Generator. As long as you use it within its limitations and you set it up for the frequency and amplitudes, and making sure that you're not really running into a lot of distortion when you're using it, I think it can be a useful little bench tool, but you just got to be aware of that.